So, then I would like to start because time is running, right? We have four amazing papers today we would like to present. The first one that we have today is the paper Panoflor, Reconstruction and Immersive Exploration of Large Multi-Room Scenes. And the presenter today is Giovanni Pintore. The stage is yours.
Thank you. Thank you for the kind introduction. Here we know that indoor virtual tours are very popular, especially panoramic virtual tours. Why? Because panoramic imagery is naturally immersive. So it is also a good choice to capture a scene using just few shots. So the point is that they are immersive, but they lack 3D information. So the representation is basically flat. Will be a problem if you try also to move around the scene, not only in a single room scene, but even if you want to represent an indoor environment more complex, like in real world where we have more rooms. So the point is that a 3D model is required in order to have a real immersive representation. And we have many single room solutions to do that in state-of-the-art works and so on, but it's hard also to scale that on a multi-room and complex and larger scene. So a multi-room navigation basically demands even not only 3D hints for stereo or to move the point of view, but even we need to know the walls, position, the doors, and even the floor level obstacle if you want to make a natural path around the scene. And the point is that in many even commercial solutions, like in Matterport, for example, so you are seeing a screenshot there, this is required a lot of efforts in terms of hardware, in terms even of user interaction. They need, for example, to acquire the scene with a scanner and then to map everything, reconstruct the model, manually modeling something. So there is a strong interest, especially in research, in trying to do it automatically. So automatically floor plan modeling is a branch, even in research now, since it's not so easy to achieve. And basically, if you look at the many papers, it requires a dense point cloud to have it. In other words, usually if you have a dense point cloud, and hence we need to have this very alienated and registered on the gravity direction in order to obtain an occupancy map, and then we can segment the point cloud in order to obtain the walls position and all the semantic information. But this is not easy to obtain in real world cases, and especially in the cases where we have mapped a very big scene. In a panoramic case, especially the typical cases like the example there, Zeta Indoor data set, that is a very real world data set, famous, similar to Matterport, we have a very sparse coverage. So we have at least 1, 2 images for each room, and then it's very hard to obtain a dense point cloud. This is the typical real-world case that we have. And in this case, the only thing possible is to have just the position of the camera. We have many important work that try to obtain the position of the camera, even accurate, even in extreme solution. There we have the case of extreme structure from motion, and also other works that try to having the position of the cameras, even using instruments like inertial positioning and so on. So we have as input several panoramic images and their position, but we don't have a reliable point cloud, a dense point cloud, so I need the 3D information. Then here in our work, we present our approach called Panoflor, that we start from a bunch of 360 images, and then we predict the dense depth map for each image. Then we have position. We reconstruct a global density map. But this density map, of course, is predicted. So the point cloud is predicted, so is noise incomplete in many parts. So we need then to reconstruct the missing structure and semantic. And so we introduce in our work a diffusion-based denoising method to do that. Then we introduce another transformer segmentation block to extract the rooms, the door, and the clutter. And then we propose an immersive stereo view with 360 transition between rooms in order to perform immersive VR navigation. Here we can see a quick example of live capture. And then in terms of technical contribution, here introduce a novel method for latent diffusion method to refine the noisy density maps. And also we introduce a novel lightweight autoencoder that is tailored to collect the indoor priors inside in order to provide encoding, decoding support for the denoising part. And then we exploit such information to build a geometric model to support the view synthesis and the navigation. So as a result, we have an end-to-end pipeline for automatic geometric and visual modeling. Here you can see the first step where we're starting from the prediction we introduce also a method to predict the depth, and then we fuse everything in a single predicted map. And here, of course, this map is incomplete. So we miss several parts, and also there are many noise from the disalignment between the depth maps. And so here we introduce the latent diffusion gated autoencoder. The difference between the typical latent foundation models is that here we are not modeling trying to generate the final scene, but we are modeling just the noise. In this way, we obtain the final denoised map as the difference of sum between the noise and the predicted map, like this. So we are, in other words, we are working trying to generate the predicted noise using our method, and then just merging the predicted map with the predicted noise, we obtain a final denoised map. Once we have that map, now we are ready to segment it. In this case, we introduce a segmentation network, transformer-based, based on a deformable deformable attention. And this step try automatically output the rooms. Rooms, I mean the polygons that define each room in each position, then the openings, the doors, and a clutter map. The clutter map comes from the prediction of the dense depth map reprojected inside the floor map. You can see there the clutter as the violet parts there. Of course, the clutter is not the modeling of the objects, but it's just a raw representation in order to predict, to have the walking space inside the rooms. And then, once we have a geometric model, we are also able to build something of visual for the immersive part. So here we exploit the geometry first to build a path between rooms through the door. So we try to avoid clutter. We have, in this case, not a learning system, but just an analytic system, very fast, that try to avoid clutter, walls, and trying to minimize also the disocclusion. So we optimize the path in order to minimize the disocclusion between different views that you have seen. So in this way, we try also to avoid parts that we are missing in our acquisition. So at the end, and then we also have, of course, the depth for each image. So using that, you can also reconstruct easily view translation and then the stereo, so both eyes, and then also slight movement inside the room. And then also we try to reconstruct the path between rooms. There we can see some example using or not using the optimization, moving from another to another room. We can see that if you move only just pointing the door, we are just crossing a lot of clutter and we have a lot of occlusion, disocclusion. And then as a result, we have a visual model that is a navigable graph that is possible to run using a WebXR viewer, using head-mounted display or using a mobile device, where in this graph we have stereo multi-center of projection views for each node, and then there we are just synthesizing slices in order to reconstruct a pre-computed representation, and also we compute a 360 video transition as arc of our graph in order to have the movement between rooms. Here we have some statistics. It's not easy to read here, of course, that we can find that in the paper. We have good performance in terms of reconstruction of the floor plan, even if you compare with standard point cloud cementation methods. We have also good using performance and also especially computational performance. If you look there, we have the comparison in between standard diffusion or lightweight method for diffusion. And also we have on the right the supervised on a test set, we have the benchmark of our method. We can see typical reconstruction, ground truth, and also you can see we are able to segment rooms, floor plan with many rooms. And on the left, the qualitative comparison, we can see even zero shoot where we have real world acquisition that are very far from our training and test sets. And even there we have good performances. To conclude, to summarize, we have presented a method for multi-room reconstruction from sparse panoramic images. This is enable immersive and real-time VR exploration. Of course, we have many limitations because we have many occluded parts, and also the view synthesis degrade moving from the original captured images. So for the future, we expect as easy to use novel generative models in order to render the transition, even in part unseen, and also to generate such part, and also to perform more user studies on this method that is on a prototypal stage. That's all. Thank you for your attention.
Okay, thank you for that very nice presentation. Do we have some questions by someone from the audience? Okay, then I would like to start with a question maybe. I have in the presentation you have shown there was like different the different inputs that you had, like and all the things I see was like looks like more synthetic data set, right? So
Yeah,
what kind of data set you have used?
Yes, it's true, because usually synthetic datasets are needed to start the training. Why? Because especially for view synthesis, you need very accurate images. So the point here is that it's possible to, especially with the noise method, to transfer the learning from the synthesis in order to use that on the real world. This is a good question because there is a lack or accurate real world data set, especially in panoramic world. There are a lot of perspective pinhole images labeled, but not panoramic images. So many methods now try to merge learning on perspective images and use that on panoramic images. Like, for example, Depth Anything or Depth Anywhere that try to propagate the learning on perspective images on real-world cases on the panoramic world.
Okay, so then I have one follow-up question. If you have used synthetic data set for training, have you also tested how it is working if you do some real-life captures, like with some 360-degree images?
You have tested. In this case, okay, it's not presented here. The point is also um, to how to align the images because as you can see, that indoor, they have also other instruments in order to align the images. Using this case, if you have many images, okay, it's easy to align in that. But if you go in an extreme solution, as it the target of or research is not so easy because we need that tool to see, for example, one image across a door in order to see the camera to have common features. So we do that. The point is that the data sets are not so big to be benchmarked in this case, but it will be a future work to do that.
Okay, perfect. Do we now have some questions by the audience? Someone? No? If not, then I would like to thank you again for the presentation and invite.
Good afternoon, everyone. It's my great honor to have the opportunity to present our work at ISMAR 2025. My name is Liu Yusen, and I'm from Beihang University, China. My teacher is Professor Zhou Zhong. Today, our paper is titled as DGD Immersive 3D Indoor Scene Synthesis via Dialog Graph Condition Diffusion. We will present through 4 main sections. First, we will address the motivation during our search on 3D indoor synthesis. Now, let's dive into the motivation behind our work. Our goal is to generate 3D scenes given the text prompt. To contextualize our approach, let's examine the existing paradigms. First, traditional scene synthesis leverage predefined scene graphs and dedicated generators. While this route is fast and can yield high quantity synthesis, it is not interactive friendly. Users cannot easily customize scene via flexible natural language input. Then, large language model-based scene synthesis takes raw text descriptions directly as input to large language models. Though it enables interaction-friendly design, it suffers slow generation speed and low scene quality. Okay. In contrast, our DGD framework addresses these trade-offs with a two-stage pipeline. Dialog graph synthesis, where an LLM converts free-form description into structured scene graphs, and immersive scene synthesis, where a multimodal denoiser generates high-fidelity 3D scenes from both graph and text. As highlighted at the bottom, DGD achieves sought-after performance in both quality and speed, while also ensuring user-friendly interaction. Let's now move to related works. Let's review related work in 2 streams. On the graph-guided scene generation side, methods like common sense and eco-scenes use structured scene graphs to drive synthesis. They can produce high-quality scenes but lack flexibility in interacting with free-form text prompt. On the text-guided scene generation side, approaches such as diffusions and holodeck takes natural language as input. While they enable text-driven interactions, they often trade off scene quality or generation efficiency. This gap motivates our DGD framework, which unify graphs structure and text interactivity while optimizing for quality and speed. Let's move to measures for our DGD framework. DGD enables continuous dialogue-driven 3D scene synthesis and editing via a two-stage pipeline. Let's walk through it. The round one is scene synthesis. Given a prompt, stage A, execute 3 core steps: perceptual, semantic grouping, and spatial functional optimization, and generates a refined graph. The refined graph then enters stage B, multi-model conditional diffusion, where graph, text, and noise are encoded, processed by multi-model diffusion blocks, decoded into a layout, and mapped to the high-quality 3D assets via shape retrieval. After the round 1, we can edit the scenes. For edit, we rerun the stage A to update the graph, see the before and after visuals, then feed it to the stage B for fast revisions. This cycle repeats for any edit, ensuring fast interaction and coherent synthesis. Next, we will detail these 3 refinement steps and denoise the network. First, let's dive into the stage A, semantic graph refinement, starting with the object extraction and scene completion. We frame the LLM as an expert interior designer to extract objects from text, classify them via a predefined ontology, identify spatial relationships, and complete the scene with structure elements. Take the example prompt, a bedroom with a bed, 2 nightstands, and a wardrobe. The wardrobe is on the left side of the bed. The model extracts these objects and then automatically adds floor and ceiling lab. The output is structured graph and object and with their spatial relationships. Next is foundational group formulation. We frame the LLM as an expert interior designer to group options to functional tools based on predefined categories. We also add intra-group spatial relationships using domain rules while preserving existing relationships. For example, the bed and nightstand form a sleeping zoo with new relationships to refine layout coherence. Next is group layout optimization. We task the LLM as an expert interior designer to arrange functional tools in a global coherent way. Following domain guidelines, it also establishes inter-zoo spatial relationships and maps them to individual objects while preserving existing relationships. As the example shows, this step enriches the scene graph with new coherent relations, readiness for stage B's diffusion-based synthesis. Now let's explore stage B, multi-modal conditional scene diffusion model. First, the diffusion process is iterating a noise to a clean scenes layout X0, producing a noise version XT. And our training objective is to minimize the L2 distance between the true noise and the model's predicted noise. The multi-model conditional diffusion block builds 3 inputs: graph embedding from stage A, layout noise, a random tensor, and a text embedding from user input. It is adapted layer norm for normalization, scale and shift for feature adjustments, and multi-model self-attention to capture the cross-model relationship. Finally, let's validate these designs in experiments. Now, let's look at the qualitative comparison. For each text prompt, like the bedroom example, we compare DG with SOTA measures, diffusions, and ecoscenes. You will see the diffusions on the left and ecoscenes on the middle have mirrors in object details marked by red cross and takes longer time. In contrast, our DGDiff generates scenes with accurate details, green checks, and run about 10 seconds, proving our achieve better quality and speed. We also show the cases of living room and dining room. We achieved the best visual results on 3D front benchmark. Now let's examine quantitative results across 3 key tables. The table 1 is main comparison. We evaluate measures on FID, FID clip, and KID for bedroom, living room, and dining room scenes. DGDiff achieves state-of-art or second-best performance across all metric and scene types. The table 2 is ablation study, removing components grades performance, validating the necessity of each part of our pipeline. The table 3 is inference time. DGDiff runs about 10 seconds per scene, order of magnitude faster than LLM-based methods like holodyke, which takes hundreds seconds, confirming our speed advantage. Together, these results show DGDiff balanced data quality and interaction speed. Thanks to the new scene synthesis paradigm we propose, we can conveniently generate and edit scene via natural language interaction, and our results can be easily imported to VR scenarios. Now, let's show a case of immersive rendering in DGDiff generated scene, plus the text-driven editing. Okay, thank you for your attentive listening. If you have any question, please feel free to communicate with me.
Yeah, there we have a question.
Thanks for your brilliant work. I'm curious about why your methods achieves faster speed, faster inference speed. Could you please give us more details?
Okay. This is our model architecture. It's based on the diffusion transformer DIT. It's have less parameters than the UNet architecture, so it is faster.
So it achieves a better balance of the trade-off between inference time and the quality.
It's not trade-off. DIT is always better than the UNite in this task. So we achieve the better quality and less speed speed. Yeah.
So in my understanding, you use the DIT for the first time in a scene generation task or some previous work.
Yeah. I use DIT for the first time, and I use a multi-model diffusion transformer.
Okay, thank you.
Thank you for your question.
Perfect. Do we have more questions? Okay, if not, then I would like to thank you again and invite the next one to come up.
Thank you for introduction. Good afternoon, everyone. I'm Taejun Kim from At3, a research institute in Korea. Today, I'm excited to present our work on real-time photorealistic style transfer of digital humans for immersive VR. Our approach transforms rendered VR images into photorealistic one while maintaining temporal consistency. Now, let's get started. Thanks to huge advances in technology, digital humans in showcases looks like real people, as you can see here. Such high quality has opened doors across multiple industries, from customer service to entertainment, where digital humans are becoming a kind of alternative to human presence. However, the reality in actual production environment is quite different. Unless you are working with AAA game studio, what we actually see in production looks more like this. There's a massive gap between showcase, demo, and what most developers can achieve. It is functional, but far from photorealistic. Why this gap? The answer is cost and complexity. Creating high-quality digital humans demands precise mesh and texture generation, sophisticated lighting design, extensive manual refinement. While this level of quality might be sufficient for certain applications, we have to ask ourselves, is this truly photorealistic? Maybe the answer is clearly no. Given this situation, our objectives were to achieve three ambitious goals simultaneously. First, Transform these production-level digital humans into photorealistic quality. Second, maintain temporal consistency across image sequences. While recent AI advances like diffusion models can generate amazing individual frames, producing flicker-free temporal coherent videos remains a significant challenge. Third, achieve all of this at VR-ready performance, more than 60 FPS at high resolution. VR demands both visual quality and speed. There's no room for compromise. These three goals might be mutually exclusive, but let me show you how we achieve all of them. As a final result, we achieve 72 frames per second at full Meta Quest 3 stereo resolution, delivering smooth, flickering-free experience. Here we see the stereo output being sent to a VR headset in real time. You can see the original rendered, and now I activate our star transfer. The transformation is applied instantly to both side views. Notice how the system maintains smooth performance as the viewpoint changes dynamically, processing both stereo views at 72 FPS. This includes the full VR pipeline, rendering, streaming, and star transfer, all at 72 FPS, not just the AI processing time. As you are very familiar, the state-of-the-art video generation models like OpenAI Sora and Google Veo 3 produce surprisingly high-quality videos. However, these technologies are designed for offline generation, taking minutes or even hours per video. They are simply not usable for real-time application. Several research have focused on accelerating diffusion models. LCM LoRa achieved good results with fewer sampling steps. Stream diffusion implements a streaming architecture for fast generation. While this approach shows significant speed improvement, but suffer from not only quality degradation, but also temporal inconsistency. Also, they still slow for immersive, high-resolution VR applications. Here is something we need to think about. The main reason why existing methods are slow is that they have large size of models. To generate arbitrary styles with prompting while maintaining quality, these models must be massive. But do VR apps need a model that can transform to any style on demand? We've become so enchanted by the magic of prompt-based generation that we may have lost sight of the actual user experience. Real applications don't need infinite flexibility. They need specific, consistent style. Games have art direction, social platforms use consistent avatar appearance. So we took a different path. Instead of universal transformation, we focused on specific, predetermined style mapping. Just to be clear, predetermined does not mean the limited. You can still choose any style you want. The difference is you choose it at training time, not the runtime. We then train lightweight architectures using supervised learning with paired dataset. This specialization is the key to our performance breakthrough. Now let me introduce the proposed system. First, we create the training pairs using diffusion models. They transform rendered VR images into photorealistic reference. Next, we train a lightweight unit to learn this transformation directly. It learns to map from renders to photorealistic styles through the supervised learning. Here you can see how the network progressively learns the transformation. Finally, we optimize the train model and deploy it for real-time VR, processing each frame independently. For application-specific training, we capture frames directly from the target VR applications. We then use a stereo diffusion with photorealistic prompts to transform these renders into high-quality reference images. This approach ensures our models learn the exact transformation needed for the specific VR environment, achieving optimal quality. For general purpose models, we use real photograph from datasets like FFHQ as input. We then also use stereo diffusion with photorealistic prompt for the dataset. To measure temporal consistency, we use two metrics based on the optical flow. First, motion deviation measure how well the transformed video follow the motion patterns of the original input. Second, flow acceleration calculate the acceleration of the optical flow in the transformed sequence alone. The intuition is simple. Flickering causes rapid change in flow direction and magnitude, resulting in high acceleration values. Now let's compare our models with existing methods. Stereo diffusion 1.5 as a quality baseline, and LCM LoRa and stream diffusion. Here we compare the three versions side by side. While stereo diffusion produces high quality frames, watch how it flickers between frames. Our method matches stable diffusion's visual quality, but eliminates the flickering completely, delivering smooth and consistent results essential for VR. Here we show four methods side by side. LCM LoRa and stream diffusion still have flickering issues, though they are better than stereo diffusion. Let's look at the quantitative quality comparison. We have measured with three different metrics. PSNR, higher is better, and SSIM LPIPS, lower is better. We achieved the highest PSNR, indicating strong pixel level fidelity. SM LoRa performed best on SSIM LPIPS metrics, with our method following closely behind. This slightly differs from visual inspection of actual images, likely due to characteristics inherent to the measurement method. Now let's talk about the performance. These are FPS measurements on a single RTX 4090 GPU across different resolutions. You can see that our method is significantly faster compared to other methods. You can also observe the extent of the speed improvement when adding 8-bit integer quantization and 4-bit rendering. Now let's see how this method performs on temporal consistency measured using our proposed metrics. Both metrics show dramatic improvement. This quantitatively confirms what we observed visually. Our approach eliminates the flickering that other methods suffer from. Beyond VR, our technique enables real-time star transfer across various applications. Here's a digital humans in a kiosk service application. The enhanced realism makes the interaction feels more natural and engaging, improving the user experience in public service applications. We can also enhance existing games without any modifications. What you are seeing here is Bethesda's Starfield game running with our enhancements applied. Using our non-invasive window capture system, we transform game characters to photorealistic quality on the fly. The processing is so fast that player can enjoy enhanced visual without any perceptual delay. Our approach is not limited to photorealistic transformation. We can train for any target style. What you are seeing is here. It's sorry, the laptop is not working yet. Okay, sorry. Let me start my program. Oh, sorry. Our final demonstration, live webcam transformation. The same technique that enhanced digital humans works seamlessly on real video input. Live webcam feed transform instantly into various styles. Without noticeable latency and flickering, this enables new possibility for video conferencing, streaming, and content creation. This versatility from VR to webcam, from render to real, showcase the broad applicability of our approach. Let me conclude my talk. We presented a real-time photorealistic star transfer technique. Our method achieved photorealistic transformation at more than 100 FPS with natural temporal consistency. Furthermore, we demonstrate its potential for development into various applications beyond VR. Of course, limitations remain. quality degrades on out of distribution content, and training still requires significant computational resources. In addition to resolving imitation, future work include introducing exhibit temporal coherence algorithm and on-device adaptation of our method. Thank you for listening. If you already registered Excel Lab Tour, please visit our demo to see what it is in action.
Questions? Yeah, there's one question. Oh, yeah, I'm sorry. You first.
Thank you very much. Really amazing work. I just have a question and curiosity about. It seems that in your you are using a quantization, model quantization, to deploy the model in the device. How much do you lose in terms of quality when you come from the original resolution floating point up to the int8 version of the models?
I'm not sure your question, but you mentioned about quantization, right? Yeah. Actually, when we apply the 8-bit quantization, the quality will be very different from the before quantization. So we use the kind of calibration data. We use the calibration data set to minimize the quantization effect, quality degradation. Yeah.
Did you evaluate the what you are losing in terms of qualitative performance, or no?
It depends on for the application specific, we sample some input data, input image to use for the calibration data. But for general purpose, actually the calibration data is not working well. So in that case, we don't use the 8-bit quantization, just use the float.
Okay, thank you so much.
Yeah.
Okay, there was one more question. We have time for one more brief question. Yeah.
All right, thank you for the nice presentation. I have a question about the 3D consistency. In VR application, the stereoscopic rendering environment in VR system, there is the 3D consistency is very important because the discrepancy between the left and right view feels like quite a big artifact, but the diffusion techniques in this paper is mainly at the 2D image space. So if the technique is used for the different view, it can be it can cause the discrepancy between two eyes. So my question is there any technical challenge to dealing with this 3D consistency, or you're just keeping it as a limitation, or future work?
Very good question. At the very beginning of this project, we also worried about the consistency between the two eyes, but the answer is there's no specific technique for match the consistency for both eyes, because our methods are very time consistent, have the very good time consistency. We don't need to do anything to match the both side consistency. But maybe there is some artifact that I may miss, but yeah, that can be our future work. Thank you.
Yeah, thank you for answering.
Perfect. So thank you again for the presentation. And I would like to invite the